So, welcome back to lectures on engineering mathematics 2. So, this is lecture number 56 and we will continue with the properties of Laplace transform. So, in particular in this lecture we will be talking about convolution theorem, very important concept which is used for getting the Laplace transform of or inverse Laplace transform of various functions. And then some limiting theorems, they are also important for instance while solving the differential equations. So, just to recall what we have done, we have gone through several properties including the shifting properties, where these two versions of the properties were discussed, and we have also gone through the change of scale property, the multiplication property. So, when we multiply by this t power n to the function, then we can just get by differentiating the Laplace transform of this f t function, and the division of by t property. So, if we know the Laplace transform of f t, then we can also get the Laplace transform of this f t divided by t by just integrating that Laplace transform. Also the Laplace transform of derivatives was discussed, and finally, we ended up in the last lecture the Laplace transform of integral. So, today we will start slightly different properties. So, that is one of them is the convolution property. So, the convolution of two given functions f t and the g t is written as f star g, that is the notation for the convolution. We have used a similar concept while discussing the Fourier transform as well, but there the limit was taken from 0 to infinity, and now we are considering this Laplace convolution integral as 0 to t f tau and g t minus tau. So, there is a shift here t minus tau, and it is integrated over d tau. So, the example we have for instance want to get the convolution of this exponential t and the function t. So, we can use this definition to compute this convolution integral. That means, we need to get e power tau, and then for the second function we have shifted here t minus tau, and we will see just in the next slide that there is a property that f star g is equal to g star f. That means, does not matter whether we shift in this g function or we make a shift in this f function, the value of the convolution integral will remain the same. So, here we have shifted in this second function g, that is t minus tau, and then we can integrate by parts because we have e power tau and this is another function. So, there are two functions, this we will take as first and this is second function. So, this will be integrated and this one will be differentiated. So, here by doing this integration by parts, we have this t minus tau as it is, the integral of this e power tau is again e power tau, and then the limits 0 to t plus this 0 to t and e power tau and this d tau. So, then we can substitute the limits of this tau here. So, if we put first the t there, this will be 0, and when we put the 0 there, so it will be e power 0, that means, we will get t from there, and again here we have e power tau and then the limit 0 to t, which will be e power t and minus 1, and there will be minus t from there. So, we will get e power t minus t and then minus 1 as the value of this convolution product or this integral f star g. Another example where we will consider here sine function and the cosine function. So, what will be the convolution of these two functions, sine omega t and cos omega t. So, f star g, again this product which is defined as sine omega t and cos omega, and there is a shift here in the argument. So, we have replaced t by t minus tau, and then this has to be integrated over d tau. We know this for trigonometric identity that 2 sin x cos y is sin x plus y and sin x minus y, that we can use here because we have sin x, and then if we treat this as sin cos y. So, we can do that. So, half, and we will get here sin the sum of the two. So, this omega tau will get cancelled, we have omega t, and then the difference. So, we have omega tau minus this omega t, and then minus minus again here this will be plus. So, 2 omega tau. So, this omega tau will become 2 omega tau and minus omega t, and then we have this d tau, which we can integrate easily, because here we have this sin omega t, we are integrating with respect to tau. So, that will be treated as constant. So, we will get tau there, and the upper limit t and minus this 0 will introduce here t there. So, but that will be substituted in a minute, and then from here also we can integrate. So, with minus sign this will be cos, then 2 omega tau minus omega t, and this 2 omega will come here in the denominator, and this was 2 there. So, therefore, this has become 4 omega, and then these limits for tau from 0 to t. So, when we put t there, this will be t sin omega t, and then 0. So, this will be 0, and similarly here we can substitute this 2 omega t and then 2 omega 0. But what we should note that while discussing this limit, the first term will be is like cos omega tau when we replace this tau by t. So, 2 omega t minus omega t will be omega t. So, we have the first term cos omega t, then the minus term. So, in front this is sitting here for omega minus, when we put tau 0, this is cos 0, we have cos omega t with minus, but cos will not read this minus. So, it is cos minus x is equal to cos x. So, here again we have cos omega t and they will cancel. So, there will be no contribution from the second term, and we will have only the first term there. That means, the value will be half t sin omega t. So, that is the convolution product of these two functions, where we have sin omega t and cos omega t. There are some interesting properties of the convolution, some of them we will list here. So, for instance, the symmetry property, that means f star g is equal to g star f, and one can observe all these properties just by the property of the integral. So, we have to take this f star g, for instance, just the proof we will go through for the first case, and the others are actually trivial. So, f star g is 0 to t f tau and g t minus tau dt, and if we substitute this t minus tau as a new variable u, that means minus d tau as du. So, the limits when this t tau is 0, the u will become t. So, this limit here will be t, and then the limit there when tau is t, that u will become 0. So, we will have a limit t to 0, but since there is a sign here with du as minus d tau. So, that will be again changed from 0 to t. So, the limit 0 to t, we have f, and this tau we have t minus u, and g t minus tau, that is again u. So, du. So, this is the integral, we have this f star g, and this is equal to g star f in the sense considering this definition. So, what we have seen here, that f star g, this integral is equal to this g star f. So, there is a symmetry, and it does not matter whether we make a shift in f or we make a shift in g, the value of the integral will remain intact. Another property, we have the so called associative property, that means, if we make a convolution product of f with this another convolution g star h, and then the convolution with f. So, in this order, that first g and h will be convoluted, and then its product with f, convolution product with f, that will be equal to, that we can do this first with f and g, and then later on with h. This will be also equal. So, similar to the property, the symmetry property we have proved here, one can also easily prove this property. And there is another kind of associative property, that if there is a C a constant, that first we here perform the convolution product of f and g, and then we multiply by this constant C, or first we multiply C to f and then make convolution with g, or other way around, that the C is multiplied to g and then we convolute with f. This is going to be the same, because the C will actually not play any role. So, this is a constant and we have this convolution integrals. So, that will come out of the integral always in each case, and finally, we will end up with like C the product with f and g. So, this distributive property also holds in this case, that f star g plus h. So, we have three functions again. So, g plus h we do, and then we make a product with this f, or we can do this f star g and then plus f star h. So, in either situation, this will be equal to the left hand side. So, these are some of the properties which we can use directly, because they are not also difficult to prove because of this integration. The convolution theorem, which is one of the important results in this section, and this says that if f and g are piecewise continuous on 0 to t and of exponential order alpha. So, these are the sufficient conditions for the existence of the Laplace transform, and then it says that the Laplace of the convolution f star g is equal to the product, the simple product of this L, the Laplace transform of f, product with the Laplace transform of g. So, the convolution is removed here, and that is exactly the use of this convolution theorem, that when we apply the Laplace transform to this convolution integral, that becomes the Laplace of f into Laplace of g. Just to give some outline of the proof here, we will start with this Laplace of f star g, that is by the definition, because this is exactly the convolution here f star g, and this f star g we have taken the Laplace transform. So, e power minus s t and dt will come with this integral 0 to infinity. So, this is as per the definition, we have the Laplace of f star g, that is given by this integral, and here it is given that f and g are of exponential order alpha. So, naturally this will exist for all real s greater than alpha. And now, if we change the order of integration here, so what it says, the area of integration, that if we assume this is t x's and this is tau x's. So, this is the line t is equal to tau line. So, the integral here says that t is varying from 0 to infinity and tau varies from 0 to tau. So, this is the area of integration in this situation, and if we want to change it now, the order of integration, that means the first with respect to t and then with respect to tau. So, first we have to fix, let us say with respect to t, that means the t will vary then this tau to infinity, and the tau will vary from, because that will be the outside limit. So, 0 to infinity. So, what we will have, the limits of tau will be 0 to infinity now, 0 to infinity at most will go to infinity, and here we have for the other one for t, that will go always from this tau to again infinity. So, these are the new limits, and now what we can just observe here, that if we take the substitution here t minus tau as u, that for the inner integral. So, dt is du, and we have the new integral now 0 to infinity e power minus s, t here is u plus tau, and then we have f tau, we have gu du and then d tau. So, we can separate it into two integrals because we have e power minus s u and e power minus s t. So, e power minus s t with tau sorry. So, f tau d tau and e power minus s u will go with g u. So, e power minus s u g u and then we have this d u. So, this is Laplace of this f t and the Laplace of g t. These are the two separate integrals now. So, it is a simple product of Laplace transform of f and the Laplace transform of g. So, this is the convolution theorem which we will see the applications for getting, for instance, the inverse Laplace transform of various functions like here. So, if you want to find the inverse Laplace transform of this function 1 over s plus 1 into this s square. So, what we have, the Laplace inverse we know for 1 over s plus 1 as e power minus t. So, there are two ways now to go with, either we can go with the partial fractions and then we can get the inverse, which we have already done before. The another approach which very often is simpler than getting these partial fractions would be this convolution theorem. So, that means we have the product of two functions here f s and let us say g s. This is given as the product of two functions. The two functions are 1 over s plus 1, the other one is 1 over s square, and we know the Laplace inverse of both of them because they are very elementary functions. So, the Laplace of 1 over s plus 1 will be e power minus t and the Laplace inverse of 1 over 1 plus s square will be t. So, we know the Laplace inverse of these two, and now we can apply this convolution theorem which says the Laplace of f star g is the product of these two Laplace transforms. Or in other way around, we can read this, that the Laplace inverse of these two. So, let us say this is f s and g s. So, the Laplace inverse of this product f s g s would be equal to the simple product of these two functions whose inverse are taken here. So, f s inverse is f t, g s inverse is g t, and then this L inverse of the product is simply the convolution product. So, here we have the product of two functions whose Laplace inverses are known to us, e power minus t and here t. So, we can apply this theorem, the convolution theorem now, and the result says that the Laplace inverse given by this 1 over s plus 1 s square will be simply the product of this f and g. So, this is the product of f and g 0 to t, then here we have taken tau and the shift we have taken in exponential function. We can do the way around as well, and then here e power minus t we can take out, and we have this tau e power minus tau which can be integrated, and we have done this similar problem before where we have just evaluated the convolution of such two functions exponential t and t. Here we have exponential minus t. So, the result will be also similar to what we have obtained before. It is e power minus t plus t and then minus 1. If we want to apply this convolution theorem to evaluate this here s over s square plus 1 whole square, again either we break into the partial fractions or we do with the help of this convolution theorem. So, again here also the convolution theorem will be useful, because we know that the Laplace transform of sin t is 1 over s square plus 1, which is seated here, and the another function is multiplied by this s over s square plus 1. So, we know that this product here is nothing but the Laplace of sin t, Laplace of cos t, and then we can apply the convolution theorem which says that the value of this inverse would be equal to the convolution of these functions sin t and cos t. And this convolution indeed for slightly more general functions sin omega t and cos omega t we have done before. So, we can quickly go through this now. So, we apply this to sin a cos b formula here again, and then we need to integrate this, and finally, what we will obtain that will be just half t and sin t. So, that is the inverse here, which with the help of this convolution theorem we have evaluated. If we do the partial fractions, so there the first and often a time taking step would be just to do the partial fractions. So, therefore, here we do not have to do the partial fractions, only we need to evaluate this convolution integral. So, it may be easier in many cases. Using convolution theorem, obtain 1 over s cube and s square plus 1, for example. So, we have L inverse 1 over s cube, whose Laplace inverse is t square by 2, and the another function here is 1 over s square plus 1, whose Laplace inverse would be sin t. So, to get the Laplace inverse of the product, we will apply the convolution theorem, which says that this will be equal to the convolution product of this half t square sin t. So, we need to get this convolution product here t square sin t, which as per the formula we have sin tau and t minus tau whole square d tau, and we can do the integration by parts. So, here this sin tau will be minus cos tau, the second this first function as it is, t minus tau whole square, and here it will be differentiated. So, 2 times t minus tau, and then this cos tau for the sin tau. And then we have, because the minus will be coming from this minus tau and the one from the this cos. So, it will be plus and this will remain minus as it is, and now we can substitute those limits by doing here also once again this by parts. What finally we will get here t square by 2 plus cos t minus 1 as the Laplace inverse of the given function. Now, we will move to the another property of Laplace transform, and these are the limiting theorems. So, they are also important to get the behavior of the function as t approaches to 0, t approaches to infinity from the information of the Laplace transform. So, these first we will go through the initial value theorem, which says suppose f is continuous on this 0 to infinity and of exponential order alpha. Moreover, it is given that f prime is also piecewise continuous and of exponential order. So, all the Laplace transform of f and f prime exist. So, suppose this f s is the Laplace transform of f t, then this initial value theorem says that the limit of f t as t approaches to 0. So, the limiting value of this f t as t approaches to 0 would be equal to limit s approaches to infinity s f s. So, we need to compute the limit, for example, this s f s, and we can get that is exactly the behavior of the function as t approaches to 0. So, this is a direct result that with the help of the given transform, given Laplace transform, we can also predict or we can get the value of the function as t approaches to 0. So, this is so called initial value theorem, and just to go through the proof of this, it is a quick proof with derivative theorem. So, we know already the derivative theorem that the Laplace transform of f prime t is s into the Laplace transform of f t minus f 0 plus when the function is not continuous, for instance at 0. So, we have to take the limit as 0 plus, which will always exist because of this assumption here that this f is piecewise continuous normally of exponential order. In this case, it is given continuous at 0 also, this f 0 will, this value will be also equal to f 0 in this particular case. So, then we have, using this derivative theorem, the Laplace transform of f prime t s L f t minus this f 0 plus, and if we take the limit here as s approaches to 0, what we will get? We will get Laplace of this f prime t. We know already that f prime t is piecewise continuous and of exponential order, and when we take this s approaches to infinity, we already discussed this before that the Laplace transform will go to 0. So, here this result follows from the earlier discussion that the Laplace transform of a piecewise continuous and of exponential order functions that goes to 0. So, here that result we have used, that this is 0, and then we have the limit here s f s, this is f s here. So, s f s as goes to infinity minus this f 0 plus, and this is the desired result, that the limit here f, this is f 0 plus, that t goes to 0 plus f t is equal to limit s goes to infinity and s f s. Coming to the final value theorem, there we have, suppose that the function is continuous, that f is continuous on the 0 to infinity of exponential order and f prime is piecewise continuous, and there is an additional condition that f t as t approaches to infinity, that also exists. So, in that case the result is that when we take this s f s again and get the limit s goes to 0, that will exactly be the value when f t goes to infinity, and the existence of this we have assumed already. In that case, this is the result of the final value theorem. Again going to the proof. So, we know this theorem, which is the derivative theorem, and now we must take a look that what will be the range of S where all these Laplace will be valid. So, here it is already given that this f is for instance the exponential order alpha, but what we should notice that this exponential order will be actually 0, because the function is continuous in including at 0, or if it is even piecewise continuous, in that case also the limit as t goes to 0 plus will exist. So, this limit exists, and moreover the limit as t in infinity f t, that also exists, and the function is continuous. So, it will remain from 0, we know that the limit exists or the value exists, and then as t approaches to infinity also this is finite, and then the function is continuous in between. So, it is actually a bounded function, and once we know that it is a bounded function, it can be bounded by this m e power 0 t, that means the order will be just 0 for this function, because it is given that the limit t tends to infinity f t exists. So, actually this result here is valid for all s. F is exponential order 0, since it is bounded, as I discussed that this limit and the two limits as t approaches to 0 and t approaches to infinity, they exist, and f t is continuous. So, it will be bounded, that means the exponential order 0. So, hence this expression here, that the integral e power minus s t f prime t d t, this is equal to s f s minus f 0. This exists for all s positive, and then having this we can apply this result, which is also a part of this discussion here. So, suppose this f is piecewise continuous indeed on this interval, and we have this f t is equal to f s exist, and moreover this integral converges, then we can actually, because this is valid for all s positive, we can take this limit there s approaches to 0 plus f s is equal to limit s 0 plus of, this is just the f s here, and this is equal to, because this limit we can take. So, the result says that this limit we can take inside, provided these conditions hold, then this e power 0 will become 1, and this value will be just 0 to infinity f t dt. So, in our case also this result is valid for all s positive, and all other conditions are also valid if we assume that the integral this 0 to infinity and this f prime t dt exist. So, having this, what we can do now, we can pass the limit here s tending to 0 from the right hand, and doing so. So, we have passed the limit both the sides here, and now this theorem, the above result says that we can take this inside and apply to this s there. That means, we have 0 to infinity f prime t dt. The result is limit s goes to 0 s f s minus f 0, and this one here, this f prime, that is f. So, f t as t goes to infinity and minus f 0 again. So, f t goes to infinity minus f 0, that is the left hand side, this is right hand side, this will cancel out, and we will get exactly this result here, that t approaches to infinity f t is equal to s f s and s goes to 0. Just a remark that in this final value theorem, the existence of this is very important, that f t t approaches to infinity. Why? If we consider this f t as sin t, we know that s f s, because the f s, so the Laplace transform of sin t is 1 over 1 plus s square. So, this is equal to 0 if we take this limit here, and in this way s f s exists as s goes to 0, and we may conclude that the limit f t tends to infinity exists, but here it does not exist. So, this final value theorem has importance. When this exists, then only the limit s f s s goes to 0 is equal to this limit t tends to infinity f t, otherwise it has no meaning. So, thus we can say that this limit is equal to L, then either this t tends to infinity f t exists and this will be equal to L, or this limit does not exist. So, if we find out that the limit s f s exists, then there will be two cases, that either that limit itself, this t approaches to infinity f t is equal to this, or if it is not the case, then limit does not exist in that case. Just a problem that without determining this f t and assuming that f t satisfies all these hypotheses of the limiting theorems, we want to compute that what is the limiting value as t approaches to 0 and t approaches to infinity given this Laplace transform. So, we can apply directly the limiting theorems, and by initial value theorem we can get this limiting value as t approaches to 0 of this s f s, and this will be 1 plus. So, s f s, if we multiply this s here, so we will have 1, and then here also we will multiply by the s there, and we will observe. So, this s and the tan inverse this a over s, and we have to find the limit as s approaches to infinity. So, this can be written as the limit s approaches to infinity tan inverse a over s and 1 over s. What we observe now, when s approaches to infinity, this is 0 by 0 form. So, tan inverse 0 is 0 and 1 over s as s approaches to infinity is also 0. So, we have 0 by 0 form, we can apply the L'Hopital rule, which is done here. So, the numerator is differentiated, denominator is also differentiated, and then where this limit, when we take s infinity, we will get only a there. So, this value is 1 plus a of this limiting value of f t as t approaches to 0 plus. Similarly, using the final value theorem, we can say that the limit f t t approaches to infinity will be limit s approaches to 0 s f s, and the value will be 1, because here s f s will be 1 plus this s and tan inverse a over s, and then the limit here s approaches to 0. So, the second term will vanish when s approaches to 0, 0 into something finite, that will be 0, and we will get just the value 1. So, we can apply these theorems for such functions, for instance. Just a final remark, that the final value theorem says that the limit t approaches to infinity f t is limit s approaches to 0 s f s if this limit exists. If f s is finite, what we should note that here, if f s is finite and s approaches to 0, trivially this is 0, because s approaches to 0 and f s is finite. So, trivially this is 0, but the why this has some meaning, because there are many functions whose Laplace transform is not finite as s approaches to 0. For instance, if you take f t is equal to 1 itself, whose Laplace transform is 1 over s. So, it is not finite as s approaches to 0. So, therefore, this SFS limit s goes to 0, we should not misunderstood that this will be 0 most of the time. No, for various functions this is not going to be 0. For instance, here we have 1 over s and SFS will be just 1 and s goes to 0. So, the value will be 1, which is indeed the function in this case. Okay. So, these are the references we have used for preparing this lecture, and just to conclude, so we have discussed the convolution theorem and some of its applications for evaluating the inverse Laplace transform, and we have also discussed the initial value theorem, which says that just computing this limit SFS as s approaches to infinity, we can predict the behavior of the function as t approaches to 0, and the final value theorem says that by computing this SFS and taking limit as s goes to 0, we can get this f t as t approaches to infinity. Well, so these are some of the important results which will be applied to various problems in applications, and that is all for this lecture. I thank you very much for your attention.